Hello and welcome to MeduHub. I am Neha Gupta, a part of your chemistry faculty, and in today's video we are going to discuss alkenes. Alkenes are saturated hydrocarbons. By saturated, I mean that there is a presence of a double or a triple bond, and in alkenes there is a double bond. The general formula for alkenes is CnH2n. Alkenes are also known as olefins. Olefins means oil forming. This is because the first member of alkenes, that is ethene, initially when it was found to form an oily substance with chlorine or bromine. That is the reason alkenes are also known as olefins. Let us see how we are going to name alkenes. So the simplest alkene is an ethene, which contains 2 carbons and 2 hydrogen. Ethene. You will see that the prefix eth depends on the number of carbon atoms. This is the same as in alkenes. Throughout organic chemistry, this will remain the same. Depending on the number of carbon atoms, the prefix will always be eth, then prop, but, and so on. In the case of alkenes, the suffix becomes ene. In alkanes, the suffix was ene. Alkanes were saturated hydrocarbons. For a doubly bonded compound, the suffix will become ene. This is ethene. If we talk about another one that has 3 carbons, CH3, CH, CH2. Now we will start numbering the carbons from the carbon which contains a double bond. 1, 2, 3. It has 3 carbon atoms. The prefix will be prop and it has a double bond. So this will be prop. Double bond starts from the first carbon. We will give the lowest number to the double bond. So prop 1 ene. Similarly, if we have a 4 carbon chain and a double bond here, H, H2, CH3. We will start numbering from this side. 1, 2, 3, 4. There are 4 carbons, so it's a butene. The double bond is at the first carbon, so we will say but 1 ene. Right? This is how we name simple alkenes. Alkenes also have some univalent groups which are derived from them. Just like in alkanes, we had alkyl groups which were formed by removal of one hydrogen, and these alkyl groups are present as branches for alkanes. Similarly, in alkenes also we can get univalent groups. Univalent groups which have the suffix enyl. Right? So if we have this group, let's say C, CH2, CH, CH2, and the branching is at this carbon here. Let me erase this. It has 3 carbons, 1, 2, 3. So it is a prop 2 enyl group. Right? Similarly, we can also have a group like this. This one is called an ethenyl group, or it is also called a vinyl group. And like this, we can find many other groups that exist which are univalent groups. Now let us move on to more complex alkenes and how we do their nomenclature. So here I have an alkene which contains a carbon double bond carbon here. You cannot start naming, you have to select the longest carbon chain, but you have to make sure that the longest carbon chain contains the double bond. So this will not be the longest carbon chain. The numbering has to start from here, and the doubly bonded carbon has to get the lowest number possible. So we can have 2 possibilities here. One is that we take this chain. If we take this chain, this will have 1 substituent. If we take this chain here, it will have 2 substituents, methyl and ethyl group here. So we pick the longest carbon chain which has the maximum number of branched chains. So this one will be our main carbon chain. We will start numbering from the carbon which has the double bond. This is 1, 2, 3 and 4. So this is a butene which has branching. At carbon number 3 it has methyl, at carbon number 2 it has ethyl. Ethyl comes alphabetically first, so we'll start with this. It will be 2 ethyl, 3 methyl, but 1 ene. Right? Let's do one more. Here. Okay, so here you will see that this compound has two double bonds. One is between these two carbons, other is between these two carbons. If we start numbering from here, 1, 2, 3, this carbon, double bond carbon will get the locant as 3, and from here if we start the numbering, the position of this carbon will be 1, 2, 3, 4. So the first double bond is getting a position 3 here and a position 4 here. So we will pick this side and this is the side from where we will start the numbering. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be our longest carbon chain. Let me highlight it. Right, this is the longest carbon chain. These are the two substituents present on it, and from here we will start the numbering. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is a decene. It has two double bonds and it has two methyl groups as substituents. Now we have 2,8. 2,8 methyl dec. Now there are two double bonds. You need to make sure that both the double bonds are encountered first. So what you do is, the first one is at third carbon, second one is at the sixth carbon. So we have 3, 6. Here we cannot just write dec, it has to be decane. Decane 3, 6 deca. 3, 6 deca diene. So whenever we have more than one double bond, it is either di, tri, tetra, ene. We need to put A here. This A has to be there. We cannot write dec 3, 6 diene. It is deca 3, 6 diene. The double bond is at the first carbon that has a double bond is 3 here. Here it is 6. So it is a deca 3, 6 diene. We have one more example. So this is a condensed bond line structure. We will count the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon chain, so it is octa. Octa, why? Because there are more than one double bonds. There are 1, 2, 3, 4 double bonds. Octa hyphen 1, 3, 5, 7, tetraene. Again, we did not write oct, we wrote octa because there are more than one double bond. There are 4 double bonds at 1, 3, 5 and 7 carbon. So this is octa 1, 3, 5, 7 tetraene. Let's see. Let's do one more to understand this concept better. Here we have one double bond here. If we start numbering the carbons 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, both ways it's a 5 carbon chain, so we can pick either of them. So let's say this is our main carbon chain. We'll number them 1, 2, 3, 4, 5. At carbon number 2 there is a branching. For the branch also you need to do numbering, so it's 1, 2 and 3. So we'll start naming this. At the second carbon there is a branch of 1 propyl group. Propyl, 2 propyl, pent, 1 ene. Or we can also write 2 N-propyl. What does N-propyl mean here? That is, it's a straight chain propyl which has branching at the first carbon, that is normal propyl. Alright. So these are the examples that we did. And through these you understood what are the rules. You need to pick the longest carbon chain first, start the numbering so that the chain has the double bond. The double bond needs to get the lowest possible carbon number, and you name the branches alphabetically just like in alkanes. So we have covered the structure and we have covered the nomenclature of alkenes. Now we need to discuss the structure. Clean all. Right. Structure. You already know that alkenes contain a double bond. So if this is an alkene, these bonds are sigma bonds. This one is a sigma bond, sigma and sigma, which are formed by the head-on overlap. This second bond here is a pi bond, right? So the sigma bond are all in a plane. The pi bond is formed by partial overlap of the pi orbitals, which are perpendicular to the plane. So we can draw them like this. So this double bond is due to the overlap of the electrons in these pi orbitals. So the rest of the molecule has a planar structure, and the double bond is a source of loosely held electrons because a pi bond is weaker than a sigma bond, right? So this is a center of rich electron density, and this bond is not as stable as compared to a sigma bond. This is the reason that alkenes are less stable than alkanes. Unsaturated hydrocarbons undergo a lot of addition reactions, and alkenes do not undergo addition reactions. Why? Because alkenes have a double bond which is formed by partial overlap of pi orbitals, and which is a center of high electron density. For such centers, reagents such as electrophiles, which are electron seeking, can attack them and give addition products. So that is the reason alkenes are less stable than alkanes and they undergo electrophilic addition reactions. We've spoken about structure, nomenclature. What about the physical properties of alkenes? So alkenes, the lowest alkenes C2 to C4 are mostly gases. C5 to C17 are liquids, and C17 onwards are solids at room temperature. They are mostly colorless, odorless, and alkenes, they burn with a smoky flame. Also, as the number of carbon atoms increase, the boiling point will increase. Why? Because the van der Waals force of interaction will increase, and hence as we move along the series, the boiling point increases with the increase in the number of carbon atoms. Just like in alkanes, if there is branching in an alkene, that's when the structure assumes more of a spherical shape. This reduces the surface area of the alkene, and because of that, the van der Waals force of interaction also decrease. And if you compare a straight chain alkene and a branch chain alkene containing same number of carbon atoms, the boiling point of the straight chain alkene will be higher than that of the branch chain alkene. So this is with structure, nomenclature and physical properties. Alkenes also undergo isomerism. Isomerism is a phenomena where a compound will have the same molecular formula but will exist as different isomers which will have different properties. So there are two types of isomerism that alkenes exhibit. One is structural, other is geometric. Let us talk about structural isomerism first. So here the two alkenes again will have the same molecular formula, but they will have different properties because their structure will be different. Structural can be further of two types, position and chain. To understand these, let me draw the structures for butene, the possible structures for butene. Here, CH2, the double bond is between these two carbons. Now the double bond can also be between these two carbons. CH3, CH, CH, CH3. There is another possibility where you need more space. Right. There is a branching here and the double bond is here. CH2, CH3, CH3. Now all of these are C4H8. All of these are butenes, but the difference is in the first one the double bond is between carbon 1 and carbon 2. In this the double bond is between carbon 2 and carbon 3. Here there is branching at the second carbon, and how will we name it? We will write it as 1, 2, 3, 2-methyl prop 1-ene. All these are isomers of butene. In position isomers, you will see that there is a difference in the position of the functional group. So if we see this and this, the functional group, the double bond is between carbon 1 and carbon 2. Here it is between carbon 2 and carbon 3. So these two show position isomerism. They will have the same molecular formula, they will only differ in the position as to that. This means that where the double bond or the functional group is present. But chain isomerism means that there is a difference in the basic carbon skeleton. If you see this and this one, you will see this carbon skeleton is a straight chain carbon. Here there are 3 carbons in a straight chain and there is branching of a methyl group here. So if you see these two, they will show chain isomerism. Similarly, these two also show chain isomerism. There is another type of isomerism exhibited, that is called geometrical isomerism. Geometrical isomerism. Geometrical isomerism is a type of stereoisomerism. In geometrical isomerism, the different isomers differ in the spatial arrangement of the atoms. In alkenes, we can safely say that because there is a carbon double bond carbon present, the second double bond is a pi bond which is perpendicular to the plane, and it is due to the partial overlap of the p orbitals. If we try to rotate an alkene around these carbon double bond carbons, rotation is restricted. It is not possible because the moment we rotate it, the double bond pi bond will break, right? So essentially an alkene will have a planar arrangement where the double bond is perpendicular to that plane. So because of that, geometrical isomerism exists where there are only 2 possible structures. One is called a cis isomer, other is called a trans isomer. It will be better understood with structures. So you look at this. This is an alkene which is butene. 4 carbon atoms, the black balls are carbon atoms. These are hydrogen atoms, the white ones are hydrogen atoms. So the second and the third carbon have a double bond. You can see this double bond is there. This carbon is attached to a CH3 group here and a hydrogen group here. This one has a CH3 group here and a hydrogen group here. So essentially all these are in a plane and the double bonds are perpendicular to this plane. In this structure, the CH3 groups or the methyl groups are both on the same side of the carbon. Both of them are at the top, both the hydrogens are at the bottom. This kind of a configuration where the similar groups, the same groups or atoms are on the same side of the carbons, the doubly bonded carbons, they are called as cis isomers. We can draw them like this. In the case of butene, both CH3 groups are on one side. Hydrogen, hydrogen. What is a trans isomer? That is the second kind of configuration that is possible, and it looks somewhat like this. Here, these 2 carbons have a double bond, right? This methyl group which was on the same side in cis butene, here we have it on opposite sides. So here it is on the top, on this carbon it is at the bottom. The hydrogen is here and the other hydrogen is here. So when these 2 groups are on opposite sides of the carbon double bond carbon, this configuration is called a trans configuration. We can draw it on a plane of paper like this. One CH3 here, other is on the different side here. and hydrogen is here, this hydrogen is here. So these are the two types of configurations that are possible in geometrical isomerism for alkenes. This is the simplest of the examples that we have taken. For geometrical isomerism, a very important condition is that there should be at least two same groups attached to the doubly bonded carbons. Here the same groups are CH3 and hydrogen. In case of cis alkenes, you will see that if we talk about their dipole moment which is due to the plus I effect of the CH3 group, can be drawn like this. Here, because it has a plus I effect, this can be drawn towards this side. These two dipole moments add up and the cis isomer has a measurable dipole moment which is mu. In case of a trans isomer, what happens? If you draw the arrows to see the dipole moment, these two are in opposite directions and they cancel each other out. So the net dipole moment for a trans isomer is 0. Because of this, you will see that cis isomers also have a higher boiling point than trans isomers. Why? Because of the dipole moment in a cis isomer, there are dipole-dipole interactions present, whereas in a trans isomer, since mu is 0, there are only weak van der Waals interactions present. Okay, so because of the dipole-dipole interactions which are stronger, what happens is that there are more interactions and these interactions have to be overcome in order for this isomer to vaporize. Hence, cis has a higher boiling point compared to trans. If we talk about the melting point, the trend is reversed. Why? Because a trans isomer has a diagonal symmetry. If you see, it is symmetric diagonally. So if you talk about a solid trans isomer, it will be packed more tightly in the crystal lattice, and hence to melt it to a liquid form, more interactions will have to be overcome, and hence this has a higher melting point compared to the cis isomer. Now what about the stability of these two? How will you account for the stability of cis and trans isomers? In cis isomers, both the methyl groups here are on the same side. Methyl groups basically are covalent bonds which are electron densities. So these two, since they are close together, they are on the same side, there will be more electron-electron repulsions. Whereas since in the trans isomer, both the methyl groups on the opposite sides, these repulsions are less. Hence, a cis isomer is less stable compared to a trans isomer. That is, the trans one is the more stable isomer. So we see that in alkenes there are two types of isomerism. One is structural, that is because of the difference in the carbon chain or the location of the double bond, and there is geometrical isomerism which tells that there is a difference in the spatial arrangement of the groups. Now one thing is very important. Many students get confused between configuration and conformation. When we spoke about alkenes had different conformations. Conformations mean that different spatial arrangement is possible because of the rotation around the carbon-carbon single bond. Okay, so when a molecule changes from one conformation to another, there is only rotation involved, no bonds are broken, no new bonds are formed. But it is not possible to go from one configuration to another configuration. Why? Because to change from one configuration to another, from cis to trans, we will need to break and make new bonds. So that is the basic difference. So alkanes had different conformations and alkenes have two different configurations, right?